So in this video, I want to discuss what we call the t-distribution and our critical values for that particular distribution. And the t-distribution is what we're going to use with our means. And so we've always talked about a normal curve, and a normal curve has a z-score or a z-critical value when you sort of calculate these inference procedures that we're doing. Well, the problem with a normal curve is that in a normal curve, we're assuming that we know the standard deviation of this curve. And that's a big problem because generally speaking, you don't know the standard deviation of the population. And we call the population standard deviation's value sigma. So the population standard deviation is equal to this value sigma. Most of the time that value will be unknown. And because that value is unknown, we generally have to estimate it. And we're going to estimate it using the sample standard deviation, which we call S of x. So we're generally going to have our sample standard deviation, which is known as S of x. And now the problem with S of x is that S of x itself leads to have a lot of error. And because of that, we need to come up with a new distribution. And this particular distribution is based off the fact that it is nearly normal. And what nearly normal means is that this particular distribution has a shape that is very Bell. It's unimodal and symmetric. And we say that it is nearly normal. That's nearly normal there when we say that, all right? So this is nearly normal. The other part about the distribution is that it has more area in the tails. And we need fatter tails because we're using this mainly for smaller sample sizes. And we know from the central limit theorem that when the sample size is bigger than 30, the distribution is approximately normal. Well, most of the time, the t-distribution is applied to when the distribution is less than 30. And because of that, we're going to check normality. And we'll talk about checking normality through a normal probability plot. But in general, the t-distribution has more area in the tails and allows for more extreme values. And then the following thing is that every t-distribution itself is defined by what we call degrees of freedom. And so these degrees of freedom, which we will refer to as df, are equal to the sample size n minus 1. And what degrees of freedom really mean is this: as your degrees of freedom are increasing, you're starting to know more and more about the population because you have more and more of the sample. So think about it, if you take an infinite number, or if you take an almost nearly number as the same size of the population, what's going to happen? Well, as you take more and more values, or as your sample size increases, the t-curve will become very close to a strict normal curve. So the t-curve approaches the z-curve when your degrees of freedom are very big. And that's because when your degrees of freedom are very big, your sample size is very big, and your sample size is approximating the actual value of the distribution. So now what we're going to do is we're going to find the t-critical value. And the t-critical value is found a very similar way that we found our z-critical value. And remember, when we do this, we use a confidence interval. And for the t-critical value, what we do is, if we want to find 95% confidence, remember we put 95% inside the bounds like this. And then we figure out how much is on the outside. And that outside is called alpha. So here your alpha is technically equal to 0.05. And you have 5% on the outside, and that means we have 2.5% to this side and 2.5% to this side. And what we do is we want to find the area on the left right here. And this is my t-critical value, or t star. And we always denote it with the degrees of freedom. Because to find t, you have to have degrees of freedom. And so in this particular case, we know we have 2.5% there with the additional 95% right here. And so remember, when we did this with the z-star, it was just inverse norm, and we added the 95 and 2.5 and got 0.975. Here, there's a function in our calculator called inverse t. So we're going to use the function inverse t here. And to do this, inverse t, you're going to do an area, which in this case would be 0.975, and you're going to give it degrees of freedom. So we need to find our degrees of freedom here. So our degrees of freedom, if n is equal to 15, recall that the degrees of freedom are always n minus 1. So if n is equal to 15, your degrees of freedom here are equal to 14. If I want to find t star at 14 degrees for a 95% confidence interval, I'm going to do inverse t, which is inverse t in your calculator is going to be menu 656. And we're going to type into there, we put that in, we're going to type in this area, which is 0.975, and our degrees of freedom, which are 14. And it will look something like this right here when you type it in. So here's what we're going to type in for that particular area. And when you do that, I get a value of 2.14. This value here is 2.145. Now, what I really want to do is I want to compare this to my Z critical value at 95%. And we should know off the top from memory that the Z critical value for 95%, Z star at 95%, well, it's inverse norm 0.975, 0 and 1 is the mean, but the Z star at 95% is 1.96. If you compare this value to this value, notice that this value is much larger. This value is much larger because you need more error in the tails. Well, what happens as you increase the degrees of freedom? So look at this next one. It says alpha is equal to 95%. So if alpha is 95% again, this is the exact same setup. I'm sorry, your confidence level is 95%. If that's your confidence level, then your alpha here is still equal to 0.05. But the only thing that's going to change now is you have more degrees of freedom. So your n was equal to 40 here. Now your n is equal to, your degrees of freedom are equal to 39. So when I find T star this time at 39 degrees, remember this will be inverse T, 0.975 again, but I'm doing it at 39 degrees. And when I do T star at 39 degrees, I get this time. I get 2.023. So notice what happened. We look compare this to the Z value again and compare it to what we just did. If we compare these two values this time, notice that Z star was 1.96, T star at 15, when sample size was 15, was at 2.14. When it was at 40, it decreased to 2.02. What happens when your T star is when your N is equal to 120? Well, again, my alpha here for 95% is 0.05. And then this time I'm going to do my degrees of freedom are going to be 119. So when I do it at 119 for my degrees of freedom, I get a T star equal to 1.980. And what's happening here is that T star is decreasing as you increase your sample size. And as a matter of fact, what's going to happen is that as you get larger and larger and larger, for instance, if you would do 1,000 degrees of freedom, you're going to see that this value for T star is going to be very close to Z star. And that's because as the sample size increases, the degrees of freedom increase. And as the degrees of freedom increase, this distribution becomes more and more normal. More and more normal means that it's going to approach its actual value of Z star.